All right, greetings everyone. I hope this video lecture finds you safe and well at home. I wanted to spend today looking at a couple of seemingly unrelated topics that are going to turn out to be related to one another. And these two topics also are sort of, well, odd in terms of the kind of topics we usually talk about in a programming class. But I wanted to talk about the notion of time and the notion of randomness. Okay? First, let's start with time. So it's a bit of a philosophical discussion worthy of some other courses on campus, as to whether or not time exists outside of humans experiencing it. But I don't kind of want to focus about the philosophical concept of time. I want to talk about time as in our need to coordinate activity between individuals and groups. Okay? Coordinating activity. And not only just individuals and groups, but also between computer systems. And that kind of coordinated activity is sometimes done asynchronously and or over a wide distance. Okay? Computers need to keep time internally in order to make this happen. Computers can and do get updates of what time it is over a network from what are called centralized time servers. Those are other computers whose only job is to help computers synchronize. But it's not generally an efficient way to always be setting your computer's clock over the network, because network traffic costs time in and of itself, time and resources. So if your computer, say, every second is trying to figure out what time it is by asking a centralized network server what time it is, then it's not not only going to always be behind, but it's also going to be eating up all your precious bandwidth. Okay? So there's two parts to this. Having hardware that executes in a constant known amount of time, that's really the central core of what computers are built around, and being able to keep or store that time information. And it's the keeping and storing of the time information that I want to kind of look at today. So, how do computers keep time? So we have to go back a little ways to sort of the nascent beginning days of the internet, all the way back to 1971. It's in that year that a committee of experts formed by the Institute of Electrical and Electronics Engineering, that would be the IEEE, you've probably heard of that group before, set out to set a consistent timekeeping standard. But what they eventually came up with was really simple. It's sometimes called the UNIX EPOCH or UNIX time. Okay? And it also is sometimes called POSIX time, and it has actually several other names as well. And there are some distinctions between these terms, but they effectively reference the same thing. The UNIX epoch consists of a single signed 32-bit integer value. Okay? Now, 32-bit, you should understand, it takes up 32 binary digits in memory. Okay? It's 32 bits long. At the time, that was pretty well the standard for computer architecture, and it is a standard that is still very much with us today, not only as part of our inherited structures for laptop computers and server-based computers, but also especially when it comes to embedded computing system, most of which are 32-bit systems, 32-bit architectures even today. Okay? So what's the deal with 32 bits, and what's the deal with the signed distinction that I'm making there? Effectively, signed means that it can contain both positive and negative numbers. So you can think of it like this. Yes, there are 32 bits in this number, okay? But we remove the first bit, and if the first bit is a 0, let's say, then this is a positive number. And if it's a 1, let's say, it's a negative number, okay? So the other 31 bits are the only bits in memory that are part of this number that can actually store the value of this number. So it's actually not a 32-bit number, it's a 31-bit number, right, with an extra bit to keep track of plus and minus, okay? Now, why would we want negative time? Well, we'll get back to that in just a second. It's this 31-bit part that's really interesting to us, okay? The values stored in that 31-bit number represent, okay, the number of seconds, okay, that have transpired since January 1st, 1970, midnight, okay, Greenwich Mean Time, okay? So that's an arbitrary point in history, okay? In fact, you'll notice that it was 1971 when this was created. They went back 1 year, back to the start of the prior year and said arbitrarily, January 1st, 1970 midnight is going to be when we start counting, okay? What we store in this number are the number of seconds that have transpired since the UNIX epoch began, okay? There's nothing special about this date except that it's an easy to remember date, January 1st, 1970, midnight Greenwich Mean Time, and everything past 1970, right, us included here in 2020, are in the positive range, but they also wanted to be able to keep things before 1970. So that's why they used a signed 32-bit number. Dates before 1970 are stored in the negative range. Okay? So we have a very simple structure for keeping count of what time it is. What, not just the time, but what day it is, right? Because we can break down seconds into minutes, and into minutes into hours, and hours into days and months, all the standard way. So by this one number, we can know exactly what time on exactly what day it is. Okay? Every second that goes by, that number increases by 1. And this is still a standard for many computer systems, especially the embedded Unix computers in many, many, many household devices. So exactly how big a number can be stored by a signed 32-bit variable? Well, that would be the equivalent of 2 to the 31st power minus 1, because we start counting at 0. Okay? And notice this is 31 bits and not 32 bits because 1 bit is used to keep track of plus and minus. That's why this is a signed number. Okay? Now, I'll let you do the math yourself. Okay? It's not too hard to do. Most modern calculators will raise 2 to the 31st power, and then you subtract by 1. But what you get is this number, 2,147,483,647. 2,147,483,647 seconds. Okay? That is, in binary, in our system, that is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, plus another one for the plus sign, 32, okay, ones in our 32-bit number. The next second that goes by, all of those ones are going to turn into zeros, okay, and that's when we have what's called a rollover error. right? Because 31 bits can only store this many seconds. And if we need to store more than that, then we need another placeholder out front of that number. We don't have it, so that gets dropped and the rest of the number goes back to 0. Okay, obviously this is going to cause an error when it happens. Okay, but not to worry. 2,147,483,647 seconds is a lot of seconds. Or is it? Because how many years is that, for instance? Well, if you do the conversion, you'll find that that is just over 68 years. Okay? And that number is well within the span of the average human lifetime. Okay, so someone born in 1970 would not have to be terribly lucky to live to see 68 years later and be there when the error occurs, right? So literally, after 68 years from 1970, that'd be the year 2038. After 68 years have transpired, many computer systems, including the bulk of the embedded systems, will suddenly not be able to keep accurate time anymore. It'll be very confusing for their operating systems as they go back to January 1st, 1970, as that last second flips over. Okay? But you can give the engineers that sort of came up with this a break. Humanity had gone from the Wright brothers' first powered flight at Kitty Hawk, North Carolina, all the way to walking on the moon inside the 68 years that led up to 1970. So those engineers probably imagined that we would have moved on, probably from even 32-bit architectures by now. And in fact, we are getting there because 64-bit architectures are becoming the norm for servers and desktop computers. There's better than even odds that the computer you're working at right now is actually a 64-bit architecture. You may be too young to remember the Y2K bug, the year 2000 bug. That bug was caused when a lot of software, a lot of operating systems didn't keep the current year except in two-digit form. And so when the year 2000 arrived, they would freak out and cause errors. Right? The fear was, and a founded fear, was that the systems that ran critical infrastructure like, the water systems, the utility systems, the power systems, those systems might crash and be largely unrecoverable all at the same time, causing widespread service outages and general chaos. Right? Luckily, that didn't happen. Okay. When the year 2000 arrived, nothing happened. In my generation, it turned into kind of a joke. Really, nothing came of it. I can speak from personal experience. When the time rolled over to midnight, January 1st in 2000, I was with a group of friends from my local youth group in Gatlinburg, Tennessee. The next day, the only thing that I saw that appeared to be broken was the software running on a Coke machine was freaking out in some kind of error state and was not accepting dollar bills or, as I recall, any money. But that was the only computer system I saw that broke down. And I can't even fully attribute that to anything other than coincidence, but it did happen coincidentally right at the Y2K bug. May have had something to do with it. So in reality, though, a ton of money and person hours was spent patching that software bug, the Y2K bug. You need to get ready because the next such bug is the Y2K38 bug, right? Remember, I said that 68 years from 1970 was 2038, okay? This is Y2K38, Y2038, okay? That is the next time when something like this is going to happen, when the UNIX epoch reaches its pre-designed conclusion, and computers, many of which still use the UNIX epoch, will be hard-pressed to not crash or show errors in their operation. And unfortunately, not only is this coming, it's also likely to be a little harder to fix than the Y2K bug. So as we get closer to that date, and you become professionals in computer science or in your fields, then you're going to not be surprised to hear more and more people talking about Y2K38, as it comes closer. Now, it's only 18 years away now, right? We're well past midway point of our 68-year window. Okay, we can actually see this working. Okay, now I've written a simple program. Let's go over here and look at it. This is just a simple program in C++. You'll notice it looks very simple and basic. It only has main. It's only got a single cout statement. It has a return statement, and then that's the end. You will, however, notice that I'm doing one thing I've never done before with you guys. I'm including the ctime library. And amongst the things that the ctime library gives us is this time function. And if you pass the value 0 to the time function, then it will give you the current time. Let's see if this works. Okay, so I'll go over here. I'm going to compile this, g++ time.cpp. Okay, /a.out. So I'm going to run it. There we go. 15854270099. 1,585,427,099. Now that doesn't look like the current time. As I sit here, it's 3:25 p.m. on Saturday, March 28th, as I record this. Wherever you are, if you run this program, you'll get a number that is bigger than this, but looks somewhat similar to it, at least in the first few digits. Okay, likely, depending on how long it's been. But it'll be a different time. How does this? Well, of course, this is the number of seconds that have transpired since January 1st, 1970, midnight at Greenwich Mean Time. Okay, let's run it again. Oh, look, that number is bigger by almost 30 seconds, right? Okay, or even more. So 1585427,146. So as I'm talking, time is transpiring. Okay, and it took me 4 seconds. 3 seconds to run those programs, right? Time is going on. And that's what this returns. This returns the current value of the UNIX epoch. Okay? All right. If you have questions about that, be sure to let me know in the discussion board. However, what I want to talk about now, I'm going to leave this behind for just a second, and I want to talk about the notion of randomness. Okay? So, random is a word that gets thrown around a lot. People are always saying within earshot of me that this or that or something or another was just so, quote unquote, random. I want you to think of the most random thing you can possibly come up with. Just think of a random thing. Think of a random happenstance, occurrence, number, anything. What is the most random thing you can think of? Okay? Now, ask yourself, was that thing random? After all, everything happens for a reason. I don't mean that to be philosophical. What I mean is that each effect is triggered by some cause, itself having been the effect of the cause prior to it. Nothing really happens out of nowhere. If I roll a dice, the interplay of the dice, the air resistance, the surface I'm rolling it on, the way it comes out of my hand, and a million other small details dictate what is going to happen to that dice. These are complicated, but everything is complicated until you understand it. How random an event is can only be explained then by the perspective of the viewer of that event. In this way, it's kind of like our notion of time, right? It's relative to the person who's experiencing it. Whatever thing we all agree is random is actually just not well understood. If someone were to understand the variables, they could easily and reliably predict the outcome. So let's take a look. I've recorded a video for you. Okay, it's a brief video of me doing sort of that paragon of randomness. The first thing we think of when we ask what is random is usually we roll some dice. Okay, so I'm going to reach for the D20. Right? That's the 20-sided dice, and I'm going to roll it. Now wait, can you guess what the number is going to be? Go ahead, take a guess. Okay, it's a 9. Did you guess 9? You know? I wouldn't have. Maybe you did. It's possible you could have guessed it. Okay? Now guess the next number. Okay, I'm going to roll it again. I got to find it. Oh, it's a 6. Okay? 9, 6. Okay, was the fact that the 6 occurred an artifact of the fact that I rolled a 9 first? Okay? Was the fact that I rolled a 6 and then a 9, is that going to determine what the next number is? Well, not so far as I know. I rolled a 17. I'm going to roll it one more time. Can you guess, out of 6, 9, 17, what's the next number going to be? Because if this is truly random, or at least random enough, then you won't be able to guess the next number. Ah, look, a 16. Okay? As far as I know, there's nothing about the previous number that tells me, right, that the next number is going to be X. Okay? Where X is some number between 1 and 20. Is this random? Well, by some definition, still no. Okay? All that random is, okay, philosophically speaking and rationally speaking, is that it's the result of a series of inputs, a series of values and variables, the interplay of which, as humans, we have a difficulty or an impossibility understanding. Okay? Does that make sense? But, as I said, if you understood the variables that went into this ahead of time, then you could easily and reliably predict the outcome. Okay? So, randomness in that sense is just an artifact of ignorance. So, for instance, your brain is a terrible random number generator. It's terrible at doing random things. There's a well-known experience that professors and researchers sometimes do that involve 2 teams that come up with a series of heads and tails, okay? So imagine that we're sitting in our classroom and I divide you into 2 teams. I say, randomly, I give one team the task, and this is blind to me. I don't know which team is which, okay? But randomly, one team gets the task of coming up with a random-looking series of heads and tail flips. Okay, so every time you flip a coin, you write an H. Every time you flip a coin, you write a T. But for this team, that team doesn't even have a coin. It just writes down a series of H's and T's and tries to make it look random. The other team has a coin and faithfully writes down H for every head and T for every tail. And let's say you write that on the board. When the teacher comes in, or whoever knows about this comes in, they will immediately be able to look at the 2 lists, and 9 times out of 10, they'll be able to tell which one is the actual random value. Why? Not because Not because randomness means that you get head, tail, head, tail, head, tail, head, tail, but because randomness means that you will necessarily get 5 heads in a row or 6 heads in a row, okay? And 5 tails in a row or 6 tails in a row, or occasionally even more, okay? Whereas you, the person who is creating a random looking list, will look at that and say, no, that doesn't look random enough, okay? So that team tends to not put long strings of heads and tails in their list. It's much more uniform looking, right? And that gives it away as not being random, okay? If I ask you to pick a number between 1 and 10, okay, then it's very likely that you'll pick 7, okay? Just looking at past experience, all right? Sometimes people pick 2. Sometimes people very rarely pick 5. That's why 7 is so good, because they don't pick 5, then they go up by 2 and they're like 7. Okay, 7. Sometimes people pick 10. I can't tell exactly, but the distribution of what numbers people pick is not uniform, okay? Which means that it's not random, right? It means it's not actually uniformly distributed over the possible values, so it's not truly random. There's another way to think about this, though. Your brain is a machine of sorts, okay? It doesn't do unpredictable. In fact, psychologists have shown experimentally that they can measure the activity of your brain when making simple decisions and determine which decision you will make before you consciously become aware that you're going to make that decision, okay? With careful enough study, with careful enough research about brain patterns, you can build in a just-in-time predictor that is going to correctly predict what the person is going to do, even if they are trying to act randomly, okay? Because you are a computer, right? Your brain, that's an imperfect metaphor, but your brain does what it does because it works a certain way, okay? So believe me when I say, even if you have trouble believing that about yourself, believe me when I say that computers cannot produce random numbers. Computers are deterministic to their core, okay? The opposite of random. We may not always understand the output that they give, but even when they appear to have acted in an unpredictable way, they haven't. They only ever do exactly what they've been told to do, and that's it. They cannot be random. They cannot be unpredictable as long as we understand the mechanisms that drive them. Okay? So what do I mean when I say random? Well, we touched on it when I talked about the dice. Okay? We touched on it when I talked about the dice. The fact that I roll there's a 20-sided dice. The fact that I roll a 6 to begin with doesn't tell us anything mathematically about the next number that's coming up. Okay? So mathematically speaking, randomness is a property of a sequence of results, not a property of a single result. A random outcome is one generated so that it was unpredictable, even considering all the outcomes so far. Unfortunately, computers still can't do this. Now, we could kind of do this with the dice, but the fact of the deal with the dice is that just like everything else, we just can't predict what the next number is going to be because we don't understand all the equations that are going into this, all the variables that are going into this. So since we don't understand that, if we ignore those, then we can say, yeah, this is random, at least random enough for our purposes, because the fact that this is a 9 does not tell me anything, does not give me any clue that the next number, I think I missed it, is going to be a 6. Okay? Computers can't do this, can't create outputs that are not driven by the previous, that are not determined by the previous input or the input to the program. A certain input always leads to a predeterminable output when we're talking about computers. So remember how I said random numbers were really ever just random from a specific viewpoint? Well, that's true here too. We've seen this video twice now, or at least parts of it. So now is it random? Before it was random, but is it now random? Because I know I'm about to roll a 9. Ba-ba! Magic. And now I'm going to roll a 6. Ba-ba! Magic. And I think I roll a 14. This is failing memory. 17. Ba-ba! Right? And 14. 16. Ba-ba! Right? Now, I didn't remember what my rolls were. But if I had, that would have been pretty amazing, right? No. Because I have seen this video before. Now it's not random. How could it have been random before and not be random now? Because I had not seen it before, right? Or at least you hadn't. It was random for me when I rolled the dice and made the recording. Okay? In this same way, computers have what are called pseudo-random number generators, or PRNGs for short. So in 1949, the father of modern computer, a man by the name of John von Neumann, invented the first pseudo-random number generator. It took a single number as input. That number was called, I'm going to write this down, that number was called the seed of the random number generator, or the pseudo-random number generator. Okay? So that number was fed into a simple program where the program would square that number and then take the middle numbers from the result. Okay? That would be your first quote-unquote random number, and that would be used as input to the pseudo-random number generator again. Those values would be squared, take the middle numbers, that's your second result, take that second result, feed it back in, so forth and so on. Okay? Is this random? Well, the series of numbers is not easily predictable based on the input, so that's good. Okay? But once we have run the program for a given seed, then the numbers that are output by that program for that seed are no longer random. Okay? So being able to argue that something is random, okay? And again, I'm using finger quotes here. You can't see me, but random, okay, means that we can't predict it. Well, if we knew more about math, maybe we could predict it. But since we don't, we can't predict it. And the last number that we used, the first number we used as input, doesn't seem to indicate anything about the next number that we're going to get out of the program. Okay? So that meets the randomness. But just like recording me rolling dice, okay, the values that come out are going to be totally determined by the input that goes in. So if we use the same input again, we are going to get the same output. It's just as simple as running a video of that series of numbers again. So it somehow loses its randomness. Okay? Now the seed we pick determines what series of values we get out. Okay? And those values are, quote, random enough, okay, unquote, because which value comes next is not easy to determine by the value that went in last. Okay? But again, they are determined by the value that went in last. Okay? So that means that they are pseudo-random. Okay? Each successive result in this manner was difficult to predict ahead of time, but each one followed, because they followed no obvious pattern, but each successive result was sort of random. It was pseudo-random. Okay? Better algorithms than the original one created by Dr. von Neumann have been created since then. But systems today still rely on merely random enough output, PRNGs, pseudo-random number generators. Okay, so let's try to write a program. I'm going to do this from scratch over here. Let's do pound include IOStream, our standard stuff. Using namespace standard, int main, okay, all right, and then return 0. And I'm going to call this, for my purposes, I'm going to save this as, I'll save it right here. I'm going to save this as random. That's probably not true. Let's do pseudo-random number generator, prng.cpp. Okay, pseudo-random number generator. All right, so in order to do this, we also need a library that has the random number generator. Okay, so the library that has the random number generator in it is called cstandardlib, I think. I just had to go look that up. I forgot what it was, so let's try it. All right, so I'm going to print out, okay, a random value using the rand, okay, using the rand function. Okay, so let's see if this works. All right, so this time I'm going to compile prng.cpp. Of course, you'll be doing this inside of your IDE. Okay, and then I'm going to run it, and I get a number. 180-428-9383. It looks kind of like our time number, although it's not. Okay. So let me run it again. Run it again. Okay. That was a random number. I couldn't have predicted that beforehand. But why do I keep getting the same random number? Well, what's the other thing you need when you run a random number generator? Okay, you need to set the seed. Okay, so let's set the seed to 5. Now, what I've just done here is I've used another function called srand. It means set the seed for the random number generator, and it's going to be 5. Okay, so let me save this. Okay, and let's run it. Nope, I need to compile it first. Okay, let's run it. There we go. 590011675. Let's run it again. 590011675. You see, the problem we're having is that whatever we set the seed to determines what the first random number is. And that first random number then determines what the second random number is, and the second random number is used to determine what the third random number is, and the third random number is used as the seed, so for the fourth random number. And so all of this whole series of random values is determined by that seed. Now, at this stage, I can't tell you with any certainty what the second, third, and fourth random numbers are going to be. So I'm going to run this program. Again, remembering to compile. And I get those numbers. Okay? Now this number is the same, 590011675, because that's the first number in the series of numbers generated by the seed 5. The second number appears to be this one. The third number is this one. The fourth number is this one. Okay? So let's run this program again and see that we get the same output. Because the seed we used determined the series of random numbers. Okay? Let's change the seed. Let's use 87 as a seed now. Will we get different random numbers than the last time we ran the pseudo-random number generator? Well, yes, we should, because, as I said, the pseudo-random number generator generates quote-unquote random values based on the sequence of values that are generated are determined by the specific seed that we use. If we use a different seed, we get a different output. But if we use that seed again, we get the same output every time we use that seed. Okay? So the seed determines the series of numbers that we're going to get, which is perfectly fine as long as we haven't seen that seed before. Okay? And as long as nobody else can guess what our seed is ahead of time. Okay? Then no one will be able to guess what our numbers are. But as you're typing this code in, you're using the value 5 and the value 87, and I've already told you to do that, so I know it's not going to be random to me what those values are. Okay? So that leaves us with a couple of questions. Practically, how do we use these seeds to trick ourselves, us, the very creators of these machines, into thinking that they are giving us random output? Output that's random enough that for all intents and purposes, or for some intents and purposes, it's random. Okay? Output random enough that it's at least hard enough to predict, that it's unpredictable enough that we're okay saying that it is unpredictable. It's no surprise. The key is in what value we use for the seed. Okay? Now, one thing that's really unpredictable then, if you think about it, is when will the code be executed? And by that I mean not in what order the code will be executed, but what time will the program be run next? Okay? Or for an already running program, what specific time was this program started? Okay? That's hard to predict. What if we could somehow use the time that the program started running or will start running next as the seed to the pseudo-random number generator? If the seed is hard to predict, then the numbers generated by the pseudo-random number generator will be hard to predict. Okay? Remember how computers can store the time as a number? Remember how a few minutes ago we were talking about that? Well, here we are again. This is a perfect use for that. What is the value of the UNIX EPOCH time right now? Do you know? I don't know. I don't know what the exact value of the UNIX EPOCH time right now is. Okay? And that's pretty exciting. More importantly, what will it be when I compile and run the next program? I don't know. That's awesome. That is a thing that is going to happen that I cannot predict. That means a value is going to be generated sometime in the future. I can't predict what that value is. And that is a value that I can use as a seed to my pseudo-random number generator. And because it's hard to predict, either looking forward or looking back, it's hard to figure out what that number was, then that's a seed that's difficult to figure out, and it's going to generate numbers that are random enough. Okay? Maybe I can use this to hide the seed, because if the seed is unpredictable, then so is the series of values that will be generated by the pseudo-random number generator. Those values might be pseudo-random, random enough. Okay? So, once again, how do I get, let's print out time 0. Okay? But in order to do that, I need to include the library called ctime. Okay? Now, this is going to give me the value of the current time right now and still use 87 as my seed. And so my random numbers are going to be the same things. At least they should be. Let's check it out. Yep. Okay. 3518975119. That's what I've seen before. I bet the next one, I bet the fourth one is 17852633737. I could have guessed that. They're right here and right here. And the next time I run it with the seed of 87, it's going to be the same. But this is what I'm going to start using as my seed now. Okay? So instead of hard coding in a value for the seed, let's use the UNIX epoch time as the value of the seed. Okay? This returns the number of seconds that have passed since January 1st, 1970 midnight Greenwich Mean Time as the seed to the random number generator. And these generate the next number in the series as determined by this seed. But because that seed is unpredictable, right? Because it's hard to predict exactly what that value will be, it's also hard to predict what the random numbers will be. So I recompile this, run it. I get a different set of random numbers. These are not the random numbers I've seen before. And also, if I run it again, I get a different set of random numbers. These are not the random numbers that I've seen before. And as the seed changes, the random numbers change. Okay? Notice how, though, if I run it twice within a second, I get the same values because this is not magic. Remember, it takes a second for this time to change. If I run it twice within that second, I get the same random number output because I use the same seed. Okay? All right, so a few practical things to remember here. Always only set the seed once in your whole program. To get truly, quote unquote, random enough random numbers, use a seed that is unpredictable. And the one easiest way to do that is to use the time, to tie it to the time when the program was run. This SRAND does not generate random numbers. It sets the seed of the random number generator. This generates the next random number in the sequence of random numbers that was started by the seed value. Okay? So are these numbers that we're seeing here, right? Can you predict them? I dare say not. But are they random enough? Okay? Remember, this first number is always really close because this is the actual time in UNIX time, UNIX epoch. Okay? But these numbers keep changing and they're random. They're random enough, but they're random-ish. But are they random enough? Well, that depends on what you need them for. So for video games, for making computers do seemingly random things, then they might be random enough. How could I predict your series of numbers ahead of time after all? Right? That's another way to answer the question, how random is this? Well, one attack that I could do to be able to jump in at some point and be able to predict what your next quote-unquote random number is going to be would be if I know about what time it was when you were going to execute the code, when you did execute the code or when you're going to, then I can pre-calculate all the number sequences for all the possible discrete time values for the time going out into the future out to some arbitrary point. Then I can check the series of random numbers you're generating against the list of random numbers I've already generated ahead of time, determine what list you're using, and simultaneously be able to figure out what root you initially had. And now I can exactly predict what numbers are next. Okay? So this can be attacked in a fairly easy, straightforward way. And so for security purposes, it'd be very bad If the reason that you're using these random numbers was a matter of high-stakes security, if you use a scheme as simple as the one that I've just described for you today, okay? Nothing is random. Some schemes are random enough, like this one, but it depends on why you need them. Some schemes are more random than others. Some pseudo-random number generators are better than others, or have less that tie the sequence of numbers together. Some seeds are more unpredictable than others. Okay? Are there better, more random ways to do this? Yes. And increasingly more complicated as well. But they all come down to this, at least in part: try to make the seed hard to predict. Okay? Okay, so the last thing we want to be able to do is get a pseudo-random number from a certain range of numbers. Okay? So what's been happening so far behind the scenes, you remember how I did this for the first time and I didn't set the seed and we still got a number out of this? Okay? The reason why is because if I don't set the seed, there's a default seed that gets used by default. Okay? Well, that's not very random. That'd be easy to predict. Okay? And what rand actually does is it returns a number between 0 and some really large number defined in the library called rand_max. Okay? So that's a wide range of numbers. What if I only want a number between 1 and 20? Okay, so I'm going to change this. I want a random number, at least we should say pseudo-random, random enough number between 1 and 20. Right now, this gives me a pseudo, I think I said 0 and 20 and some random number. I think it's actually 1 and some random number before. This gives me a wide range of numbers between 1 and like the maximum number, a really big number defined by the library. Okay? How do I take a value between 1 and some really large number and constrain it to a range between 1 and 20? Well, enter our old friend, the modulus operator. Okay, let's see if this will do 12 mod 2. Okay, what does that mean? 12 mod 2 equals 0. Okay, what about 13 mod 2? 1. How about 14 mod 2? 0. Okay. What about 79 mod 2? Okay, can you predict what the answer is going to be? If you said 1, you were correct. Okay? We've already seen the modulus operator used in this way before. Now, in code, remember the modulus operator in C++ is the % sign. We'll see it in just a second. But what modulus does is it returns the remainder of dividing the number by this number, the larger number by this number. 79 mod 2 means give me the remainder of dividing 79 by 2. If this number is odd, then the remainder of dividing by 2 will always be 1. If this number is even, the remainder divided by 2 will always be 0. That's why 12 was 0 and 14 was 0. Okay? But notice, this value 2, when this is the thing we are modding by, always has a result between 0 and 1. Okay, what if we do 14 mod 3? Okay, we're going to get 2. What if we do 14 mod, let's do 15 mod 3. 0. All right. 16 mod 3, 1. 17 mod 3, 2. 18 mod 3, 0. So it's like 0, 1, 2, 0, 1, 2, 0, 1, 2, right? If you take a sequence of numbers, you're always going to get, and if you do mod 3, you're always going to get 0, 1, 2, 0, 1, 2, 0, 1, 2. The values, the possible values of dividing by 3 and getting the remainder, the possible values of the remainder of dividing by 3 are always 0, 1, or 2. In fact, in general, okay, if you take any number, say any number x, and you mod it by a number n, then the possible values for all values of x are 0 through n minus 1. Okay? 0, 1, 2. 0 through 2 for when you're doing modulus by n. Okay? So, how big... Sorry, it is 0 to a maximum number. I'm sorry. So how big is this? How many values is this? Okay. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20. So that's 20 values that we want to include. Okay, from 1 to 20. Now, if I do this, what are the possible values I'm going to get? This is some large random number. Okay? It's some whole number. Okay? If I find the remainder of dividing by 20, then what are the possible values I can get? Well, any large number, any large whole number, modulus 20, are going to have possible values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, or 19. And those are the only possible values when modding by 20. Okay? Those are the only possible ones. Notice that 0 through 19 is really close to 1 through 20. So if I take the result of this equation, okay, which I know will be some number between 0 and 19, and I add 1 to it, then I must necessarily get some number between 1 and 20. Will it be a random number? Yes, because this number is random. And as a random number, I cannot tell you exactly which one of these 20 values it's going to map to. But I can tell you that it will be one of these 20 values when I do modulus 20 on that random number. And then when I add 1, then I'm going to get values between 1 and 20. I'm going to get one random number between 1 and 20. Okay, let's see if this works. Let's run it. Okay, I'll recompile it, run it. I get a number 17. Okay, I rolled a 17. I rolled an 18. I rolled a 10. I rolled a 16. I rolled a 13. I rolled a 20. I rolled a 15. As you write this code for yourself and try it for yourself, you will not get this series of numbers. Or if you do, I'll keep going, okay? Because it doesn't seem like the further we go, the less likely it is that you're going to get the same numbers. Okay? Why? Because this is generating a random number that is tied to the time of day, the date and time that I am running this program. And you will be running it at a different date and time, so you will likely get a different random number to start with. And when you do this, you will make that number, you will map that number between 1 and 20, but it will be a different random number. Okay? All right. So, to test our skills with this, I have put up a assignment on Canvas. I think it's going to be assignment 15. It's the assignment. It's the next assignment that come up. That'll be due. I don't know. I haven't decided yet. I'll tell you on Canvas when it's due. If you have questions about that, please hit me up in either email or on the discussion forum. And I hope, again, that you're safe and sound, and I will be hearing from you soon. Okay, thanks. Bye-bye.